Um, okay, sure. All right. Hello, everybody. Thank you for coming to the PhySU Undergraduate Colloquium. Our speaker for today is Barsam Rahimi, and his talk will be an introduction to Tensor Calculus and applications in physics. Please enjoy.
Thank you. I have. Right. Okay, welcome everyone. So my goal today will be to give a introduction for understanding what are tensors a little bit again. How do we use tensors? Why do we use tensors? And we're going to talk about some applications, specifically to the theory of general relativity. Yeah. So what I want to start with is where do we use tensors? Why do we need to learn about them? And as we progress through the lecture, you'll see more of why they're important. But to give you an idea, they are very, very frequently used in fields like electrodynamics, quantum field theory, relativity theory, or even in fields like mechanics of solids, fluid dynamics. So they're very helpful to know. And in a lot of fields, necessary to know. And some examples of tensors are the Riemann curvature tensor, the metric tensor, the inertial tensor, the electromagnetic field tensor. If you don't know what those are, don't worry. We're going to talk about a couple of them. And the way I want to get started with this is talking about a problem which I hope most of us have seen before. So this is a graduate level physics problem, and it is, can you show the system of equations of forces for this mass on its inclined plane if it is in equilibrium? And most of us have seen probably this problem before, right? And there are different ways to approach this. Usually, you can either take this x-y axis and write down your force equations, some of forces in x, some forces in y. Another way you can approach this is taking a different set of axes, and you say, okay, I don't want to work with this. I'm going to take the surface of this inclined plane to be the x-axis. So I'm going to call it x prime. And I'm going to take this line perpendicular to it to be the y-axis, so y prime. And obviously, you're not going to get the exact same looking equations. But when you actually put in numbers, you'll find that these are the same, they give you the same numerical results. And my question is, why is it that when we transform, it seems like you have different equations, but they're still representing the same physical phenomena? And if you know the answer, please don't say it. And to understand that, I want to dive a little into this. So if you've done some linear algebra, you'd know that we have rotation matrix, which if we're rotating a vector by some angle theta clockwise, then this would be the rotation matrix for it. And so this would be the matrix for the transformation that takes your system of forces in xy and take it to x prime and y prime. And now the question is, how do we know that these do represent the same thing without punching in a bunch of numbers, right? Because if it was just like that, then half of the 7 millennium problems would be proven by now. And the answer is, let's say I'm going to draw this a bit bigger here. Let's say this is my x, y axis, and this is my x prime, y prime, okay? These look the same. I'm going to say they're not the same, so you believe me. And I take this line segment, okay? I'm going to call this S. And I take it into this x prime, y prime, and I get, let's say, something like this, okay? Now, if the length of this segment S in S prime is reserved, then numerically, you measure this with xy, and then you measure this with x prime, y prime, there wouldn't be any difference, right? So S must equal S prime. in terms of length or magnitude of S. And now if we use some trigonometry, so we say this is some dx and this is dy, then this looks like the Pythagorean theorem. So some infinitesimally small distance, ds, squared equals ds prime squared. And now what you would do is go ahead and instead of saying ds prime, you substitute in the transformation that you get from this. So you get x prime equals x cosine theta minus y sine theta, and y prime equals sine theta, x sine theta plus y cosine theta. So what you're going to do is go ahead and write ds prime squared as dx prime squared plus dy prime squared. And then instead of saying dx prime, you're going to write this expression and square it. And once you add them, you find that it does indeed equal dx squared plus dy squared, which is ds squared. I'm not going to go through that because that's very time consuming, but you can check that for yourself. But to understand on a deeper level, why is it just that this line segment works? How about vectors? How about a set of vectors? How about higher dimensions of vectors? To do that, we have to first go through a little bit of math, and then we can understand this in a much deeper level. So we're going to work on some notation. These are called tensor notation. So I'm going to take the set of my standard unit vectors, E1, E2, E3, and I'll say, okay, this is too much work writing all of these over and over again. So I'm just going to go ahead and represent it with EI. Okay? So if I have some vector with components A1, E1 plus A2, E2, then I can just write this as a summation over some index I from 1 to 3 of AI times EI. Right? And now I introduce another vector, B. B1, E1 plus and this, again, can be represented with the same summation, but I'm going to use a different index just so we don't mix it up. Actually, let me just M and N for reasons that we don't know yet. Okay, so I condensed this all notation into this. Now what I'm going to do is I want to take the dot product of these two vectors. And you will see why in a second, why I'm interested in doing that. So the dot product of A and B. If we go just forget about these, what would the dot product of A and B look like? Can someone tell me? Yes? Exactly. You just take this times this, plus this times this, plus this times this, correct? And the dot product of two vectors would give you a scalar, so the dot product of two vectors is a scalar. So I'm going to represent this now with our summation notation, and let's see where it takes us. Of AMBN times the dot product of our unit vectors. Okay? And now you might say, okay, well, this looks like the dot product, right? These would normally just be either ones or zeros, and then you'd have the dot product. But this object here is actually something that I said its name, which is represented with GMN, and this is our first tensor, and it's called the metric tensor. Okay, this is a very, very, very important tensor. So if I were to rewrite the dot product, it would look like this, using the metric tensor. Okay. And here instead of writing two summation signs from 1 to 3, I just said summation over m and n. We know we're summing over from 1 to 3 because a and b both have 3 components. So you may ask, well, why do I need to know about the metric tensor? And we'll find out in a moment. But first, let's say, how do we know that this can become our ordinary dot product? Because the dot product that we're used to, it's just a sum over m and n of am times bn, right? And this is only when m and n are equal. So the way we get to this is by something called the Kronecker delta. And if you know what the identity matrix is, then you're not going to have any problem understanding what is the Kronecker delta. Because it is very, very similar, not the same, but similar to the idea of the identity matrix. It is represented by a lowercase delta, and its definition is it is 1 when the indices match, and it's 0 when the indices don't match. Okay. So our ordinary dot product is just this expression where the metric is equal to the Kronecker delta. Okay. Now, let's go back to the idea of distance, which I erased. Oh, I probably shouldn't erase that. Let's say that I am in some sort of axis. Okay, so curvilinear coordinates. Okay, because why not? And I want to find the distance between these 2 points. Okay, so one way to go about this is say, okay, if I just take one infinitesimally small distance, right, and then I sum over it, then that would give me the distance from this point to this point, right? And that's a more calculus topic. But how can we use this stuff that we just built here to make this? Well, let's go to the Pythagorean theorem. The Pythagorean theorem tells us that ds squared is dx squared plus dy squared plus dz squared. But that's only when we have flat coordinates and coordinate axes. So how can we adjust the Pythagorean theorem to a more generalized curvilinear system? And the way we do that is using the metric tensor. So I'm going to write this as another form, and then we're going to talk about what does it mean. Okay, so this is a generalized Pythagorean theorem. And this here, we actually know what this is. This is our good old tensor notation. But what we did was say, okay, instead of x, y, z, I'm going to use x1, x2, and x3. And if that's too much, I'm just going to write the whole thing as xm. Okay? So this is just the same thing if, let's say, m is 1 and n is 2. Then what is dx1? That's the same thing as dx. What is dx2? That's the same thing as dy. So this would be dx dy. Okay? And the metric tensor is the set of coefficients that would go behind these products. So in this case, can someone tell me what do you think is the metric tensor in this case? So let's look at the coordinates. What is the coefficient here? 1, exactly. What is the coefficient here? 1. And the same thing here, it's a 1. So our metric tensor is actually just a diagonal of 1s. Oh. And off-diagonal components are a 0. Okay? And we can replace this with the Kronecker delta. But let's say, what happens if these are not 1s? What if, let's say, this is x squared? Well, then this would just have an x squared beside it. Right? Obviously, it won't be true for this coordinate, for the flat x, y, z coordinate system. But in curvilinear coordinate systems, you don't know what's gonna be thrown at you. So this metric tensor allows you to use the form of Pythagorean theorem to calculate distances and scale your units so that it gives you the correct distance with respect to those curvilinear coordinates axis. And so you can, if you ever visit your high schools or if you see anyone that hasn't learned about this, you can just tell them, oh, do you know what the Pythagorean theorem is? And they say a squared plus b squared equals c squared. Say, no, it's actually ds squared because gmn times dxm dx. Okay, I'm gonna bring this to this side. So now let's go back to the first question. What's a tensor? Again, very non-mathematically rigorous way of thinking about them is think of something that generalizes the concept of a scalar and a vector. Okay? So if we go back to the idea of how we transformed from one xy axis for inclined mass on a plane problem, we had a transformation rule, right? And it was that rotation matrix. Now, the way we denote how the force vector transforms, because obviously force is a vector, I hope we know that. The way we denote how this transforms is using a transformation rule. And let's say I have a force whose ith component, okay, in the prime reference frame is equal. Now I'm going to throw the transformation at you, and then we're going to talk about what does it mean. The summation over, let's say, Q. It's a P. Oh my god. Oh, not a B. It's an F. That is a transformation rule that our force vector follows from the prime frame to the unprimed frame. Okay, so we know what this is. That's the pth component of f. So if p is 1, then we're talking about the x components. We know what this is. Well, what is this? That's a really weird thing, right? All this is saying is, if you recall that transformation rule, this is saying take the derivative of x prime with respect to x plus take the derivative of x prime with respect to y plus take the derivative of y prime with respect to x, take the derivative of y prime with respect to y, and you multiply those to the component of the vector. Now, if you write all of this out, so write down the transformation rule and then work out the derivatives, you'll see that it makes sense and it gives you the exact same result that you would get if you were to do it in xy. And these transformation coefficients allow us to know how does our vector transform. And now we said, okay, if vectors are a form of tensor, then if I have a tensor, let's say PQ. So now this is a rank 1 tensor. This is a rank 2 tensor. Okay? And a scalar would be a rank 0 tensor. Then the way this would transform is by the following transformation rule. And you might say, okay, but how does this tell me what's a tensor? And it's a bit of a weird way of thinking about it, because I'm going to tell you that this does tell you what a tensor is. Because whatever object you have that has two indices, so if you have a square matrix, and if it transforms according to this transformation rule, then you can say that it is a tensor. Okay? So an example of this would be take the metric tensor and see, does it actually transform as a tensor? And if it does transform as a tensor, then it's a tensor. Okay? So that's the definition. Okay. All right. Okay. Now this is a physics talk, so let's talk about physics a little bit. Why do we need all this math for? And let's start with planes. Not planes like the two-dimensional stuff, but planes that fly. Does anyone have any questions about this or want to? Okay. Yeah, don't forget to like and subscribe. Okay. So okay, let's say I have two people, Alice and Bob, okay? And Alice believes the Earth is a sphere. Bob says no, the Earth is flat and it has turtles under it. I don't care which one is correct. That's not where I'm going with this. Let's say that, well, hopefully we know the Earth is a sphere. Let's say a plane wants to go from New York to, I don't know, Moscow. Great time. If you were to go from here to here, just by looking at it, how would you get there? What is the path that you're going to take? The shortest path, right? The straight line. Okay, simple. Now, who has ever had a spherical map that you can open and look at? You can open up the map and look at it. No one. It's always a plane, right? When was the last time you were in your car and I was like, oh, let me take out a globe and look at it. Where are we? So when you're on a map, there was a problem, because when you actually put, let's say, a tracker in the plane and you look at the path that it takes, you'd expect it would go something like this, right? Because that's the shortest path. But the problem is that when you actually look at it, it takes a path something like this, I think. What is happening? Why is this doesn't look like the shortest path that would minimize the use of fuel, right? So why is the plane taking this path, whereas the straight line? And more importantly, why is this a straight line here but not a straight line here? The answer is that a sphere is what we call intrinsically curved. If you don't know what that means, don't worry about it. A sphere is a curved surface. It is curved, wow, and a plane is flat. And the problem is that when you take something from a curved surface to a flat surface, you're gonna lose something about it. In this case, you lose the path. And if you've done topology, then you know a lot more about this than I do. Okay, so how do we know which one's correct? Well, we know the Earth is a sphere, so this one is the correct one. How do we relate this, and how do we calculate these paths is a problem that relates to general relativity, relates to geography, or using how GPS systems work. And that's what we're going to do right now. And that's the idea, this is called the idea of geodesics. Okay. And now, before telling you how do we calculate these geodesics, let's talk about relativity. So in relativity, we have an inertial reference frame and a reference frame that is not inertial. An inertial reference frame, you are not accelerating. Okay, that's the simple way of putting it. So if I have a position vector for myself, then my acceleration must be 0, correct? But the problem is that in relativity, we don't have vectors with component x, y, z. Because the theory of special relativity, which I'm not going to get into, is basically tells us that space and time cannot be treated as separate things, but they should be one thing, which we call space-time. And in space-time, when you have vectors, they're called four vectors. And they would have not just the x, y, z component. These are just tildes. I'm just saying them so we don't confuse these with this. But you would also have a time component for your vector. And so instead of saying that this position vector, and this is in R4, okay, you gotta say that the derivative with respect to the proper time is 0. And if you don't know what proper time is, again, that's in special relativity. I'm not going to get into it. We can talk about it after the lecture if you'd like. Okay, so we have this, but how do we make money out of this? How do you get something out of it? And the answer is we use the chain rule. So I'm going to say that this is the derivative of this same expression. Now, what is this x mu? Okay, that's the Greek letter mu. The thing is, here you have derivative with respect to coordinates, right? These are the set of coordinates. Remember, x0, xy. Oh, well, I should have said here that if you use the Greek index, then you also have the time components, and t is x0. Okay, so you're just taking derivatives with respect to coordinates, and then this would be your coordinate velocity, okay? And this would be 0. And if I use the product rule, then I get something like this. Okay. So now we have two coordinate derivatives here. We have our acceleration, and we have these. Okay. Now in a second, I'm going to get rid of both of these. Okay. Let's first get rid of this. Okay. Remember, again, you have to keep this picture in mind that these are just the derivative of a vector with respect to some coordinates. Okay. And the coordinates are these. And we can put this, like the collection of all these derivatives, in one big matrix, right? And if we have all these derivatives in this matrix, then let's call it A, then linear algebra tells us that if you multiply a matrix by its inverse matrix, then you get the identity matrix. No, identity matrix. So again, this is a very non-rigorous part. I'm going to multiply it by this. Oh. And I'm going to call this the inverse of A. Okay? So multiplying both sides by this, we get something. Oh. Okay, and if you're not familiar with these dots, they just mean time derivative. Okay, so when you put 2 dots, it means second derivative with respect to time. One dot means first derivative with respect to time. And now this, again, if you read the handout, it's going to be a lot more detail. You can understand why we can do this. But I can just write this, because this is a matrix of 1 on the diagonals multiplied by this. I can just switch these indices and get rid of mu. And now we have this term left, okay? And this, again, there's a lot of stuff about this term. All I'm going to go into is this is called an affine connection, okay? And it's represented by a gamma. So in this case, it would be gamma mu nu. And the reason why I didn't include alpha here is because alpha is being summed over. So really, there's a summation here about alpha, and this is called the summation convention. When you have an index that's repeating upstairs one time and one time downstairs, you assume that you're summing over it, so you no longer write the summation sign. So since alpha is being summed over, when you actually write out the summation, you're just going to get a bunch of numbers added to each other, and in the end, they're not going to have an alpha index. So it would make sense for the object representing this to not have alpha as an index, but just mu, nu, and lambda. Okay? And this would give us this equation. And this is called the geodesic equation. Okay. So this is what you would use to calculate those paths. So that's the first part of the physics. And now the second part is about the Einstein Field Equations. Does anyone have questions about this? Would you like to ask right now? Okay. So I'm not going to derive the Einstein Field Equations because that takes way too much time. I have derived it in the handouts. The Einstein Field Equations is really a way for us to use F equals ma, but in all types of reference frames. Okay, so hopefully we remember this well. And let's think about gravity. Okay, Newton gives us this equation. And this is his equation for gravity. But the problem is that these don't, well, there's a lot of problems with these, but how do we know there's actually a force between the two objects? Why should mass have a force? And why does that work? And really, the underlying equation behind this is something from classical mechanics, which is called the Poisson's equation for gravity. Now, there's a lot of, there's this fancy symbol here. You can just think about this as the second derivative. Okay? This is the gravitational potential. And this is energy, oh my god, density. Okay? So this equation basically says the gravitational potential and energy are correct. Yes. That's a rho. Yes. Sorry. Yes, so the question was, is this a P or a rho? And that's a rho, because we're talking about density. Okay. Thank you for the clarification. What this equation tells us is that gravitational potential and energy are related to each other. Okay. And if we know, there's one thing about Einstein that I'm pretty sure everybody knows is this equation, which is like half of the thing that he actually wrote. And all you got to take about this is that energy and mass are kind of the same thing. Okay. So from this reasoning and this reasoning, then we know that gravity and mass are somehow related. But how are they related? And more importantly, how are they related in a relativistic context? So let's think about what does it mean to have gravity. Now, Einstein tells us that instead of having two bodies exert a force of gravity from God knows how long of a distance on each other, and that keeps everything together, Einstein says, okay, if I have an empty space, right, then my space-time is flat. It's like a plane. Okay? So basically I have this picture, and you have flat lines. But then if we put a mass in the space, so this is a very famous demonstration, like take a cloth and put a ball on it that's really heavy, that's going to curve your space-time. Okay? So if you have, let's say, the sun here, then your space is going to look something like this. And excuse my artistic skills, I'm more of a music person. Okay? And so really, what is happening? Because you just have mass. And to understand why this is related to gravity, we think about Einstein's happiest thought of his life. I'm going to change it up a little bit. So imagine when you're skydiving, okay? When you're skydiving, you don't feel your own weight. And that's because gravity by nature is, in a way, an acceleration, right? When you accelerate downwards with an acceleration of 9.81 meters per second squared, you say force of gravity. But if you don't feel your own weight, does that mean you're not experiencing gravity? And the answer is that that's not what you should think about when you think gravity. Gravity is just an effect. But what kind of effect? Let's say I want to go from this point to this point. Okay? Imagine yourself on this. Like right now I want to go from this point, from here to my back, over there. This is the shortest path, and it's a straight line, correct? What Einstein says is, when you have a mass in your space-time, it curves those straight paths. So this would be something like this now. And obviously it's not a straight line, right? However, because of the curvature of the space, in this geometry, this is the shortest path. So if you remember this, here, this is a straight line, this is the shortest path because we're on a spherical geometry. But when we take that into a plane, it doesn't look like the shortest path. And that's because we're in a completely different geometry. So when you have mass, it changes the geometry. It creates curvature in your space-time. And so it bends these straight line paths to curved paths that are in this geometry, the shortest path. And now, if you're skydiving, then all you're really doing is following those straight line paths in space-time. And following those straight line paths is, oh my God. Following those straight line paths is really what we call gravity. So when you're, let's say I take a parachute and I jump out of this window. I'm going to fall down, but that's not because there's a force of gravity on me. Gravity is not a force. Gravity is the effect of following straight line paths through space-time that is curved. And the reason for that curvature is because of the presence of this mass. Okay? That's really the main takeaway of this lecture. And now the question is, how do we calculate this curvature? And the answer is the Riemann curvature tensor. The Riemann curvature tensor is even better than any tensor we've learned about so far because it has even more indices. Okay? So 4 indices, the more the better. And, well, again, this is something I can't cover in this time, but the Riemann curvature tensor basically has what's called contractions. And what contractions does is really condense your information into a lower dimensional, lower rank matrix. So through some process, which is discussed in a handout, you can get a rank 2 tensor, and you can even distill this down to get a scalar. And this is called the Ricci tensor, and this is called the Ricci scalar, or the curvature scalar. Okay, so let's think about how can we adjust this equation here using these tools that we have to accurately model gravity. Well, on the left side of Einstein's equation, we should have something that talks about gravity. And we said that gravity is just a curvature in space-time. So if we have something that tells us what's curvature, then that's going to be a good left-hand side for Einstein's equation. And as it turns out, the left-hand side is the Ricci tensor minus 1/2 the Ricci scalar multiplied by the metric tensor. Okay? Now, again, if you want to really understand where this comes from, you have to learn something called the covariant derivative and a bunch of other stuff, which is covered in the handout, not here. What about the right side? The right side talks about energy, right? So we use a tool called the energy momentum tensor, T mu nu. And it happens that this right-hand side would turn to something like this. And because we've related energy to curvature, and because E equals mc squared, so we have related the presence of mass to curvature in space-time. And so this equation, this is called the Einstein Field Equations, not the equation. This expresses the dynamical curvature of space-time in the presence of mass and energy. And what is this equation? Why did I say field equations? I only wrote one equation. This is because, again, these are indices. All of these, you can think about them as matrices. So this is actually a set of partial differential equations. And the aim of the partial differential equations is to solve for the metric tensor. And once you solve for the metric tensor, which is extremely difficult computationally, once you solve for the metric tensor, you come back here to the geodesic equation, and you can use the metric tensor to calculate geodesics. And the way you do that is because there's a fine connection right here, is actually not exactly the same, but kind of the same as something called the Christoffel symbol, which is also represented by gamma. And the Christoffel symbol is a combination of the inverse of the metric times first derivatives of it. Okay, that's not what it's equal to. That's the form of it. Okay, and you can use this and the Einstein field equations to calculate geodesics, and that tells you the shortest straight line paths in space-time and how do bodies move in a curved space-time. Now, one note before we finish is that if you have taken classical mechanics, then you'd be familiar with the least action principle. And the least action principle says the system minimizes the action, and then you vary the action, and then you find the Euler-Lagrange equation. In general relativity, there is the Einstein-Hilbert action, which is given by this integral. So here, R is the curvature scalar, G denotes the determinant of the metric tensor. And kappa here is 8 pi g. Of course, this is in natural units, where c is equal to 1. But if you were to not do it with natural units, then you'd have a factor of c to the 4 here. Okay. Yeah. So I hope this was a kind of okay introduction to understanding how does general relativity work, what's the difference, why do we need tensors, how do we use tensors, and what's the whole relativity thing that everybody's talking about. Thank you. Questions or yes? Yes. Yes, sure. Does anyone have questions?
I have
Yes.
But it is not really related exactly. But you're talking about how, when you're falling in a gravitational field, you don't feel your own weight. And I've seen that's because inertial mass and gravitational mass are the same thing experimentally. Has all of your reading about this revealed any more detail about why that might be the case? Even though I know in general we don't understand why that is true.
Right. I don't have much information about that part, but what I can say is that it's just a completely different way of looking at falling because in a classical mindset, then if you jump off of a building, then you're just saying, oh, gravity's pulling me down. But relativity says that you're just following a straight line path in space-time. So we're not really even talking about what is your mass. Of course, that does matter, but the way we think about how does gravity work is different. Any other questions? Yes?
Can you just connect the last bit you were talking about the least
Okay, so the question is, how can I explain the connection between this least action principle and the metric tensor? Okay, so the least action principle, this is a thing in classical mechanics. So the action that the system takes, which you can basically use this actually to derive the geodesic equation here. I'm not going to go back to it. You know which one I'm talking about. So you would use the least action principle, and this metric you would have to know from the Einstein Field Equations, right, in order to calculate the paths.
that describes this, the action that
yes.
the system is taking.
Yes. Again, the action, it would require like a background in classical mechanics to understand what is actually the action. What do we mean by it? Yes. Right. Okay, so the question is, can I clarify what is a tensor exactly? And okay, this is a kind of weird way because we're not really used to defining objects like, oh, if it moves like this, then it's this, right? In your head, the way you can think about it is, okay, how can we generalize this concept? Okay, I have a scalar, I have a vector. How are these related together? Or an example of like a tensor would be the inertial tensor. And the inertial tensor would relate the angular momentum to the, oh, I forgot. We're gonna cut that out. So, think about it like a higher dimensional generalization of scalars and vectors. So, like a scalar would be, again, would be a rank 0 tensor. So, if you remember, we don't put any index for scalars, right? For vectors, we put one index when we were doing dot product. I don't know if I still have it here or not. No, I don't have it. Anyways, like I say it here, f, like I have one index here, right? And then I say, okay, rank 2 tensor would be something like this. And this, you can, if you think of it from a linear algebra perspective, a scalar would be like a 1x1 matrix. And then a vector would be a column matrix. So then this would be a square matrix, right? Now what happens if I add another index? Exactly, a 3D matrix, yeah, like a cubic matrix. Yeah, and then what happens if I add 4? Then it's going to be stacks, and then that's out of my imagination. Okay, does that make sense? Okay. Really, computationally, this is what you need to worry about. Like, if it obeys this rule, you can say that your square matrix is a tensor of rank 2. Okay. Okay. Yes. Okay, so the question is, if tensors really are like a generalization of vectors and scalars, then can we write vector equations and scalar equations in terms of tensors? Am I right? Yes, and the answer is correct. Yeah, you can do that. And I don't have like an equation off the top of my head, but you can look at Griffith's Electrodynamics. In the end section, there's like a whole like relativistic electrodynamics section. And there he talks about how you can write like vector equations instead of tensors. He introduces all this tensor notations again. And he shows like how do you write relativistic like Maxwell's equations and all those sort of stuff. So yes, you can. Any other? Yes? Oh, that's a really good question. So the question is, why would one introduce tensors in the first place? And the reason is here. Okay, I know this is a very ugly thing. The reason we want to use tensors is because let's think back to the idea of okay, I'm going to erase this. Let's go back to the idea of mass on an inclined plane. Okay. So this is obviously a set of vector equations, but we said vectors are a form of tensors, right? Now, if we use tensors, then it obeys that ds squared equals ds prime squared. You agree? So what this allows us to do is, since we know all these transformation coefficients that we have, given the transformation rule, because we know we can calculate these transformation coefficients, we can find, okay, how does our tensor change? How can we rewrite the form of the set of equations that represent this if I have some sort of curvilinear axis and I have the mass on an inclined plane here, right? Because now you can't just use like flat geometry. The geometry is, well, the geometry is the same. You can't use the same xy coordinates, but because you have a transformation rule, you can calculate these coefficients and they would allow you to know how does the tensor transform from one to the other. So in a way, in a sort of physics way to think about it is, okay, tensors allow us to build frame independent equations. Okay, so for example, if I have some tensor is equal to 0, this is true in all reference frames. Tmn is in all reference frames equal to 0. Doesn't matter what kind of curvilinear coordinate systems you use. Okay, does that answer your question? Thank you. Does anyone have any more? Yes. The Riemann curvature tensor, yes.
So is that, you were talking about it in connection to like Einstein and gravity? Are you saying that basically it describes like the curvature due to gravity, and then also by distilling it down, that have to do with like how we classically see the world?
Okay, so the question is, sorry, yeah, go ahead. Oh, okay, so the question is, does the Riemann curvature tensor, is it related to gravity? Am I right? And
my question is, when you were talking about that you could also like distill it down, does it have
Yeah.
to do with how we can like think of the world as curved space-time as well as thinking about it in a
I see. Okay. So the question is, if we can distill the Riemann curvature tensor down, is that related to how we can think of like a curved space-time as like a 2D plane that we see locally, correct? Okay. The reason why we can do what you're saying, like think about the world as a flat plane in our frame, in our like perspective, it's a topology question. Okay, so if you're, I'm going to draw it much bigger. If you're, let's say you're living on the sphere. Actually, I have a bit of a demonstration, let's say, for this. Say you live on the sphere, right? In topology, if you have, this would be a manifold. And a manifold, you can think of like a generalization of surfaces. Okay? If you're on this manifold, on a manifold, you must. Okay, how can I explain this? When you're on a manifold, locally, if you're on the manifold, right, you would see everything as a flat plane. That's just the property of manifolds. That's how manifolds work. Okay, so, and again, if you remember before the lecture, that space-time in the topological definition, it is a 4-dimensional, skip one word, manifold. Okay, because it's a manifold, you see yourself like we're on Earth and we see a 3-dimensional world, right? We have X, Y, Z, but really we live in 4 dimensions. But because we're on a manifold, we perceive it as 3 dimensions. Because if I tell you, okay, move forward, move back, move right, move up and down, you can do that. But if I tell you, okay, can you go 15 months to the future? Can you do that? No, but time is one of the dimensions in this 4-dimensional Hausdorff manifold. So the answer to the question is, it's related to the topology and what are manifolds. Yes. Yes. This, the Einstein Field Equations? Yeah, so with the Einstein Field Equations is what we use to replace this, because this tells us that gravity is acceleration. But this equation is a different idea of gravity. This equation tells us no, gravity is actually the presence of mass or energy in a curved space-time. So what you're saying, if we can write this as Fi equals MAI, that is correct. Well, that is basically like saying the x component of F is mass times the A component, because the x times the x component of acceleration. That's why we're writing Newton's second law component by components. Whereas this is just it's different. It tells us that gravity doesn't work. It's not a force between two objects. It's due to the curvature that those masses create in the space-time that you tend to fall down when you jump. Yes. Mm-hmm. 16 set of partial differential equations. I'm not sure about why the notation is like that. I believe it just has to do with how because this was the work of Bernard Riemann and Gauss, and I guess they decided it's a capital R. But yeah, the metric tensor is always lowercase g, because actually if you use uppercase G, you can sometimes see this form of Einstein field equations, which is oh my god, where's the eraser? Like if you go on Wikipedia right now and you Google Einstein field equations, this is what it's going to give you. So again, we said kappa is just this coefficient here. And this G mu with the capital G is called the Einstein tensor, and it's just the left-hand side of the Einstein field equations. So these are equal. And the reason why this exists is because something called the contracted Bianchi identity, which I've covered in the handouts. And it's basically a set of identities about the Riemann tensor that you use to derive the Einstein field equations. Solve for the metric tensor, yes. Sorry? Yes, this equation here, right? Yeah. Yes, so the question is the goal, after you solve the Einstein field equations, is the goal to put it into this? And the answer is yes, because when we solve the Einstein field equations, again, it's a partial differential equations, which we solve for the metric tensor. Once you solve for the metric tensor, you substitute it into this geodesic equation. And remember, the geodesic equation tells us those straight line paths in that curved spacetime. Okay? And the reason, well, you might ask, where am I putting the metric? I don't see no metric tensor here, right? And that's because this idea of Christoffel symbols. And Christoffel symbols are I'll just write the formula for it. I don't have the formula memory. It's too many indices. A Christoffel symbol is defined as this object, basically. So this is a Christoffel symbol, and these are just derivatives, okay? This is just a shorthand for saying this, okay? So the Christoffel symbol and the affine connection, again, they're not, mathematically, they're not exactly the same objects, but they're very, very, very close. And so you use the Christoffel symbols here instead of the affine connection. And by solving for the metric from the Einstein field equations, you can calculate the Christoffel symbols. And then these would just be your coordinate derivatives. And so this would allow you to calculate these paths for curves in spacetime. Yes. Sorry, where? Here? Oh, that was just a joke. That was just a joke. Yeah. It just means it's a higher rank tensor. So remember the Riemann curvature tensor is a rank 4 tensor. So what it is stacks of 3-dimensional matrices. And yeah, that's basically it. Yes. Okay, the question is, can you have an infinite dimensional tensor? The answer is, you can ask the math departments about that.
Okay, I think that is all the time we have today, unfortunately. So thank you, everybody, for coming. Thank you so much, Barsam, for giving a great presentation. Feel free to grab some cookies on your way out. We will have another presentation at 5 p.m. next week, as always. And then we will be taking a break the week before reading week because we are having our Halloween event. And so that would be a conflict. So we don't want to conflict with that. That's a big event for us. I encourage you all to attend. But next week, you should go to the Colloquium again. We will have the announcement up over the weekend. And I think we will bring out the hot drinks for that one. So we'll have a tea or hot chocolate or something like that, like a kettle here. So, okay, thank you all very much for coming. I hope you enjoyed. I certainly did. Okay, thank you very much, Barsam. And the handout will be available in the description of the YouTube video, and I'll post it on the Discord. I'll just edit the announcement for this Colloquium, and I'll include a link for that. Okay, so thank you very much.
Thank you.
Big round of applause.
Thank you.